Euclid, also known as Euclid of Alexandria, was a Greek mathematician often referred to as the father of geometry. Little is known about Euclid's life, as there are only a handful of references to him. Fortunately, Euclid was the author of Elements, a collection of 13 books consisting of geometry and other mathematical domains which preserved his theories. One of the most famous Pythagorean proofs of all time is Euclid's first geometric proof. His proof uses the well-known bride's chair, peacock tail, or windmill image to portray that the sum of the squares of the legs of a right triangle are equal to the square of the hypotenuse. While this proof is well known, it is not necessarily easy to understand. Therefore, we are going to walk you through each step of Euclid's thought process.
To visually help our explanation of Euclid's proof, we thought it would be best to use GeoGebra. In the center of our figure is a right triangle ACD. Drawn behind each side of the triangle, we drew the squares that Euclid imagined. He used these to help find half the area of the smaller squares and compare those values to half the area of the larger square. Euclid then used the proposition that states if a parallelogram and a triangle have a base in common and are in the same parallel lines, then the triangle is half the area of the parallelogram. From this proposition, we are able to identify the area of the triangle CDF to be half the area of parallelogram ADFC, because both shapes share a parallel line DF and AE. At this point, we can also note that the area of triangle CDF and triangle ADF have the same area value of 4.5 units squared. Next, Euclid compared triangle CDF to triangle IDA. Since both the triangles have the same side lanes, we know their areas will be the same. Euclid then constructed a line parallel to segment ID and going through point A. We labeled this segment NO. With this parallel line, he was able to use the same postulate as mentioned before to state that the area of triangle ADI is half the area of parallelogram NOID. Thus, we can show that triangle NID is congruent to triangle ADF. Both in this example have an area of 4.5 units squared. Next, Euclid went on to prove that the area of triangle HCA was the same as the area of triangle CKN. He repeated the same process as used before to prove that triangle ADF and NID were equivalent. Taking into consideration that our audience understands how to compute what we just did, we will continue on to explain Euclid's proof. Now that we have shown that triangle CKN and triangle NID are equal to half the area of the squares HCAG and ADFE, we can visually see that triangle CKN and triangle NID make up half the area of the full square CDIK. This concludes the bride's chair proof that half the area of one side square plus half the area of the other side square is equal to half the area of the longest side square.